Hello. When day-side reconnection occurs, solar wind energy enters into the magnetotail. Then magnetosphere responds to this excessive energy in its three modes, sometimes with steady magnetospheric convection, sometimes with substorms, and sometimes with Sawtooth events. And the last magnetospheric mode is the topic of this presentation. A Sawtooth event is a, I'm sorry. A Sawtooth event is a repeated injection of energetic particles at geosynchronous orbit. Here I showed one Sawtooth event with 4 teeth. In each tooth of Sawtooth events, we have two phases. The growth phase, which corresponds to a slowly decrease of energy flux, and the expansion phase, which corresponds to sharply increase of energy flux. Since more than 94% of Sawtooth events occur during geomagnetic storms, likely storm times condition drives Sawtooth events. One of these conditions is increasing oxygen density and pressure in the plasma sheet, because these density and pressure of oxygen increases during geomagnetic activity, and especially during the storm times. These observations arises a hypothesis which says the increased oxygen ions in the plasma sheet can derive Sawtooth oscillations. Brambles first could produce Sawtooth oscillations after including oxygen outflow in the LFM global model. In his simulations, the period of Sawtooth oscillations was between 2 to 5 hours. But what is the source of oxygen ions in the during in the Brambles oscillations? Here I showed that oxygen ions in the plasma sheet come from two sources in the ionosphere. They can come from the night side region of aurora if oxygen ions travel along the magnetic field lines. Also, oxygen ions can come from day side cusp when convection is sufficiently strong. In another study, Brambles divided Sawtooth events in two groups of ICME-driven Sawtooth and SIR-driven Sawtooth. And he realized that only for ICME-driven Sawtooth events, he needs to include oxygen ions in the LFM global model. In this figure of his paper, the concentration of oxygen ions in the ICME Sawtooth event is in the night side region of aurora, and for the day side, the concentration is in the for the SIR events, the concentration is in the day side region of aurora. Ouellette showed and suggested that alpha-venic energy in the expansion phase enters into the night side region of aurora and derives more oxygen outflow. Then this oxygen outflow reach themselves to the plasma sheet and accumulate here. The pressure increases, and we will have the next substorms. In another model, Varney included oxygen outflow in the growth phase, which its concentration was in the night side region, and he could simulate Sawtooth oscillation. His model was under steady solar wind conditions. But we have another paper which shows that having only 10% of cusp oxygen outflow in the plasma sheet is sufficient to have Sawtooth oscillations. Also, we have one observational case study which is done by Eric Land. He looked at the source of oxygen ions in the plasma sheet and also in the tail during ICME-driven Sawtooth and SIR-driven Sawtooth, and he saw that the main source of these oxygen ions is cusp day side. To study the importance of day side and night side outflow and Sawtooth events, we address 3 questions. How does the outflow change after Sawtooth injection time? Is the dominant outflow on the day side or night side? And how do SIR and ICME events compare? To answer these questions, we used fast and specifically Teams recalibrated data. we performed a superposed epoch analysis to analyze the variation of oxygen outflow flux relative to injection time and during each tooth. We used a list of Sawtooth events, which was produced by Kai and Cloer. This list contains 45 SIR and 54 ICME-driven Sawtooths during a period of 10 years, but we only used those fast orbits which we could clearly find their auroral boundaries. Then we calculated oxygen outflow flux in the energy range of 10 electron volt to 12 kilo electron volt and outside the loss cone angle. We averaged this oxygen outflow flux and mapped it over a 300 kilometer altitude. I showed this data along the fast trajectories and used it in my epoch analysis study. This is one of the fast orbit which I used it in my study. First, I used Anderson method to find the auroral boundaries. Here I showed the equatorward auroral boundary in purple and the poleward boundary in green. So this region is the auroral region. Here is the day side auroral region, and here I found the night side auroral region for this orbit. Also, I showed the onset time with the vertical red line. So for this orbit, the day side auroral region is for before injection time, and the night side auroral region is for after onset time. Also, in the bottom plot, I showed the mapped oxygen outflow flux over 300 kilometers. In the dial plot, I showed the fast trajectory, and this mapped oxygen outflow flux is shown with colors along the fast trajectory. Here I showed the oxygen outflow flux, which I calculated from our recalibrated teams data, because our team in the UNH could calibrate teams data. I used this data, and here I showed all the data that I have in a 10 years period. I binned my data into 3 epoch times. The left column shows half an hour before injection time. The middle column shows the first half an hour after injection time, and the right column shows the second half an hour injection time. The top row for all the ICME Sawtooth events, and the bottom row is for SIR Sawtooth event. And as I said before, I showed the outflow flux along the fast trajectories. The location of the dial plots here in this slide will repeat in my next slides. For each auroral pass, I binned the auroral pass into 3 latitude segments, like here. Then I averaged outflow flux in each auroral segments and showed the values the values of outflow flux for each segments here. In the next steps, I did another average over these 3 segments and assigned the new number as the auroral average segments for the whole auroral path. More than that, I binned my magnetic local time into 4 sectors. The night side sector is in the right, and the day side sector is in the left. And this location of night side and day side is constant in my next slides. Okay, now I want to look at the variation of outflow flux of oxygen in the night side sector. Here I showed the night side sector with the thicker black lines, and I used auroral averaged oxygen outflow flux. In this line plot, I showed the median of oxygen outflow flux in the night side sector as a function of epoch time. Red color is for ICME and blue color is for SIR. We see that the oxygen outflow flux increases after injection time in the night side region of Aurora for ICME and for SIR Sawtooth events. And also we see that oxygen outflow flux is more intense in ICME Sawtooth events than in the SIR Sawtooth events. To have a closer look at the night side region of aurora, I looked at the average outflow flux in auroral segments. And here in the line plots, I showed the median of oxygen outflow flux in the equator-ward segments in the top. Then I showed the median of outflow flux in the middle segment and in the poleward segment. We see that in all auroral segments, oxygen outflow flux increases after injection time in the night side region of aurora, and the maximum of this injection time after the outflow flux after injection time occurs in the equator-ward segments of aurora in the night side region. And for the cusp day side, I used auroral average oxygen outflow flux, which is shown with the thicker black lines here. And in the day side and in the line plot, we see that for ICME Sawtooth events, the oxygen outflow flux decreases after injection time, while for the SIR Sawtooth events, we see a slightly increase. And again, we see that ICME Sawtooth events have more oxygen outflow flux in the day side region than this IR Sawtooth events. Also, I looked at the day side versus night side. I used for the ICME in the top and for the SIR in the bottom, I used yellow color for day side and purple color for the night side. We see that the day side outflow is highest before the Sawtooth injection time here and here. But after injection time, the day side and night side outflow are about the same here. And the outflow is higher during ICME storm than SIR storm in both in the day side and in the night side. Okay, what I showed here. I showed that before the Sawtooth injection time, the cusp outflow is the strongest. So the cusp is more likely involved in triggering the injection. But after the Sawtooth injection time, the night side outflow increases significantly. This is consistent with the injection driving more outflow. And the conclusion is this. Thus, both day side and night side outflow may be involved in creating the Sawtooth injection mode. Thank you.
Thank you very much. So we're now in open discussion. A question on the chart. So how did you account for varying EUV radiance during the study event?
EUV radiance during this study. Actually, I didn't look at the EUV numbers.
Okay, so next one. The flux seems to much lower than that modeled by Lambrus et al. Is the altitude for the mapping same?
I don't know.
Okay. Any other question or comments?
Actually, if you know, I think the Brambles used fast oxygen outflow. I don't remember that he mapped it over 300 kilometer, but mapping over 300 kilometer of altitude should show more outflow. So I think at least he should show the less outflow than me.